This slideshow is about the composition of magmas and igneous rocks. What we want to explain is what are the processes that cause such a variety of igneous rock magmas and ultimately igneous rock compositions. We see things in the crust that range from mafic in composition all the way to silicic in composition. Well, how do we create all these different compositions of igneous magmas and igneous rocks? Remember that we can describe the continuum of igneous compositions along a range that goes from one end member we call ultramafic to another end member we call silicic or felsic. The ultramafic end member, remember, is rich in the elements iron and magnesium and calcium, while the silicic end member is rich in silicon and sodium and potassium. And just as an ultramafic magma is rich in these three elements, iron, magnesium, and calcium, it also is correspondingly poor in the things that are enriched in the silicic magma and vice versa. So ultramafic magmas, we can say, are enriched in iron, magnesium, and calcium and somewhat depleted in silicon, sodium, and potassium. And the opposite is true of silicic magmas. They are rich in silicon, sodium, and potassium and relatively impoverished in magnesium, iron, and calcium. Now, for the purposes of illustration in this slideshow, I've created a color scale to show the composition of the magma, and that's what I've shown here. So it ranges from deep blue, which represents ultramafic compositions, to bright yellow, which represents silicic or felsic compositions, and intermediate compositions show up as some form of green. Now, it's worth noting that just as we can describe the composition of igneous rocks or magmas with this on this scale, we can also describe the composition of individual minerals. For example, a pyroxene shown here, here's the formula of the pyroxene. You can see that it's a mineral rich in iron, magnesium, and calcium. This is in fact a mineral that's enriched in the ultramafic components, and so we can consider it an ultramafic mineral. In a similar way, we can consider an alkali feldspar, which has got the formula shown here that has potassium and sodium silicate, that this mineral is enriched in the silicic or felsic component, so we can consider this mineral to be a silicic or felsic mineral. So let's see what happens when a magma cools. Now, the most important point here is that as a magma cools through its liquidus temperature and on then to its solidus temperature, during that interval of temperature where it's continuing to crystallize and more minerals are forming, the early form minerals, the minerals that form closer to the liquidus, tend to be more mafic than the minerals which form at lower temperatures closer to the solidus. So as it cools, the initially formed minerals tend to be more mafic, and the later form minerals tend to be more silicic. So we can sort of show what that looks like by showing a little cartoon of what a crystallization sequence would look like. So at first, the liquid crystallizes some amount of a very iron-rich mineral, an ultramafic mineral. Perhaps that's olivine, perhaps that's pyroxene. And as that mineral is extracted from the melt, notice that the remaining liquid's composition changes. It changes to become slightly more silicic or felsic. As additional mafic and ultramafic minerals are extracted from the melt, the residual melt once again is driven towards more silicic or felsic compositions. And finally, the final crystals that form tend to be the silicic ones, and they complete the crystallization sequence then by converting the final liquid into solids. And when we're done, we have a rock which has the same average composition, has exactly the same composition as the liquid that it started with, but now that composition is comprised of different minerals with radically different chemical compositions. Some are essentially ultramafic minerals and some are essentially silicic or felsic minerals, but in combination, the average composition, when you take all those minerals and take into account their abundances, is the same as the initial composition of the liquid, which is shown here by this black line. Now, you know exactly then how this works when we imagine the process of partial melting. Remember, you've been told that when partial melting occurs, the partial liquid that's produced is always one step more silicic than the original rock. Well, here you can see why it happens. So this is the original rock, which has an average composition right in the middle of this compositional spectrum. And as it begins to melt, the first minerals that are going to melt are going to be the ones that are silicic or felsic. So as those minerals melt out, that creates a liquid which is more silicic than the original composition. It's got a composition down here near the silicic or felsic end. And if we then tap that liquid, we squeeze that liquid out and extract it, we will have extracted out a liquid which is more silicic than the original composition of the rock. That's how partial melting works. We can also show how that happens on this diagram you've seen before as well. So this sort of summarizes what happens with partial melting. We start out with a rock of one composition, and when we partially melt it, we generate a liquid of a composition that is one step more silicic. So ultramafic rocks melt to mafic liquids, mafic rocks melt to intermediate liquids, and intermediate rocks melt to silicic or felsic liquids. Now, if you understand how the process of partial melting works, you can also understand how the process works in reverse when we start out not with a rock that's going to melt, but with a liquid that's going to crystallize. So here we have what represents a pile of liquid. There's no solids at all, and this liquid has sort of an intermediate composition somewhere on our compositional spectrum between the most mafic and the most silicic end members. And we're going to allow this liquid now to begin to crystallize. So as we discussed before, the first crystals that are going to form at the highest temperatures will tend to be ultramafic. And as those crystals extract ultramafic components from the magma's composition becomes slightly more silicic, slightly more yellow here. If we continue to precipitate additional mafic or ultramafic minerals, they will continue to extract iron, magnesium, and calcium components from the liquid, driving the liquid even further towards the silicic or felsic end member. So we have a magma here that's been partially crystallized, but notice that the residual liquid here now is a more silicic composition than the original liquid composition, which was once again given by indicated by that black bar, which shows that its initial composition was right in the middle of the compositional spectrum. So we've taken a liquid and we've partially crystallized it. And if we once again tap off that liquid and move it somewhere else, we will have created a liquid which is more felsic than the original liquid through the process that we call crystal fractionation. So crystal fractionation is the partial crystallization of a magma, and then the physical extraction of that residual magma, which creates a magma which is more felsic than the original magma. Once again, we can show that on this diagram here, but now everything's happening in the row that corresponds to magma. So if we start off with one kind of magma, say an ultramafic magma, and we partially crystallize it, we undergo crystal fractionation, we can produce a mafic magma, and then further it can be converted into an intermediate magma, and even through further crystallization, it can even end up creating a silicic or felsic magma. So how and where do these processes happen inside the Earth? Once again, let's remember that originally in the mantle, through either hydration melting or decompression melting, the peridotite mantle rock undergoes partial melting and generates a mafic liquid. That liquid, that is the primary magma that's produced inside the Earth, inside the mantle. That magma generally will rise due to buoyancy towards the surface. Now, what happens to it next can get quite complicated. Often, what happens is that magma fails to penetrate all the way through the crust because it reaches a density barrier. The magma has some kind of density, and if the crust has a density less than that of the magma, instead of passing through the crust, will accumulate underneath the crust, between the mantle and the crust, and pool in some kind of large magma chamber at the base of the crust. Within that magma chamber now, it's sitting there, it starts to crystallize as it cools off, and as it starts to crystallize, it can undergo crystal fractionation, which can convert this originally mafic magma into something more silicic, perhaps an intermediate magma. In addition, this magma is hot, and if the rocks in the crust have a lower solidus temperature than the temperature of this magma, then those rocks can be heated to the point where they will undergo partial melting. So this is heat transfer melting, shown in this sort of yellow envelope here. And the heat from this pool of hot mafic magma can and often does partially melt the overlying crust due to the heat it provides. That partial melting then produces an intermediate or even silicic magma, which can rise to the surface either to erupt as a volcano, as shown here, or in some cases it rises but then again stalls out to density, as shown in these other little pods of magma here, which have simply risen and just stalled because they can't rise any further. Within these little stalled pods of magma, we can also get crystal fractionation occurring, or if this magma is still hotter than the solidus of the surrounding rocks, we can also induce partial melting of the surrounding rocks and generate an even more silicic magma in the surrounding areas around these little pools of magma. So through this process, we're starting with a mafic magma down here in the deep magma chamber shown in red, and we're generating successively more silicic magmas either by the process of crystal fractionation or by the process of partial melting, either by this originally mafic magma or by its products, which are rising up and stalling within the crust as well. Should also note that it's possible in some cases for some of this mafic magma to escape from the magma chamber and rise all the way to the surface without any kind of modification at all. In that case, we'd actually have eruptions of mafic magma on the surface instead of the more intermediate magma shown here at the volcano, or perhaps even the silicic magma generated by partial melting of the crust around this stalled magma body. So I hope you get the idea of how we can create this enormous variety of compositions of magma by combining these two processes which change the composition of rocks and magma. Crystal fractionation, which changes the composition of a magma, and partial melting, which extracts a more silicic or felsic magma from a rock of a given composition. And taken together, then those magmas can rise, they can mingle, they can themselves fractionate, and together then they produce an enormous variety of compositions of magma that exist in the crust.